Para dar continuidade à terceira palestra da manhã, a gente vai ter o professor Frederic Michard, que é um médico intensivista que talvez os mais jovens não conheçam, mas ele basicamente inventou o Delta-PP, tá? Nos anos 2000, tá? E ele é um entusiasta de tecnologias na UTI, tá? Então, a gente o convidou para participar desse debate. Ele é bastante conhecido por suas publicações sobre gerenciamento de fluidos, monitorização hemodinâmica, e atualmente está trabalhando bastante com IA, ok? Hello, Professor Michard. Can you hear
Hello.
me?
Yes. Can you hear me as well?
Yes. I'd like to thank you for your presentation, to be here with us. Thank you very much, and be free.
Thank you
You
so
can
much
begin.
for the invitation. It's a pleasure to give a lecture in your event, during your event. So you invited me to speak about AI in critical care or for critical care. It's a pretty broad topic, so I decided to focus on hemodynamic monitoring and management for two reasons. First, I mean, this is a topic I know best. And second, you will see we start to have a significant number of studies discussing the potential value of AI for hemodynamic monitoring and management. So before I start, I need to disclose the fact that I'm today leading a consulting and a research group based in Switzerland, where we focus on digital innovations with medical applications, but we do not sell any medical device. So I'll start with blood pressure monitoring. You probably already know that today we can get information about blood pressure from pulse oximeters thanks to artificial intelligence. So we all use pulse oximeters to measure SpO2, and we get, I would say, for free, in addition, a pulse oximetry waveform. And so if we use a machine learning algorithm, we feed it with a large number of pulse oximetry waveforms and the corresponding blood pressure values, because during the development phase, we're going to monitor blood pressure continuously as well. And then the algorithm should be able to learn to recognize specific features or specific patterns associated with either a rise in blood pressure or a drop in blood pressure. So you may have seen studies like that one. I mean, this one is just an example from my colleagues from the University Hospital of Lausanne in Switzerland. They used a pulse oximeter. They used a machine learning algorithm to track changes in blood pressure during anesthesia induction. And as you can see on the left-hand side with systolic arterial pressure, or on the right-hand side with mean arterial pressure, they were actually able to track pretty well changes in blood pressure during anesthesia induction and during the subsequent tracheal intubation. So the concept is the following. For patients in whom you use a brachial cuff for blood pressure measurements from time to time, in addition, from the pulse oximeter, in the near future, I think we'll get information about blood pressure trends. And so if the blood pressure drops, then it will automatically trigger a new blood pressure measurement with the brachial cuff to confirm the blood pressure value, but also to recalibrate the machine learning algorithm. So I think these kind of tools should be available within the next few years. There is no existing product today for anesthesiologists or intensivists, but there are already on the market some wristbands, like that one, I wear one right now, which are able to give you blood pressure numbers after an initial calibration, of course, but that gives you blood pressure numbers every 30 minutes, every hour, just from the optical signal. A second topic, which is pretty interesting, and you may have seen many publications on the topic, is the prediction of hypotension. So again, the idea is to use a machine learning algorithm, but this time to predict, to forecast what's going to happen, what may happen in 5, 10, 15 minutes. This is what we call predictive analytics, or the science of prediction. You may have seen this paper from the group of Maxime Canesson, published already 6 years ago, about these HPI, these hypotension prediction index, predicting that the blood pressure may drop in 10 to 15 minutes. And what has been proposed following this publication and a few others is that when this HPI is above 85, then you can bet that the blood pressure will likely drop, and then be proactive. As a matter of fact, when you look at the ROC curves that were built to assess the predictive value of HPI to predict hypertension 5 minutes, 10 minutes, or 15 minutes ahead, you see a pretty large area under the curve. But first comment, you look at the best cutoff value. It's pretty far from the 85 cutoff value, which has been proposed by the developer. The best cutoff value is somewhere between 35 and 40. On the top of that, we know now from a significant number of publications that the predictive value of HPI has been overestimated, at least in the initial validation studies. That is related to selection bias. It's really, I would say, a high-level discussion. I don't have the expertise to go into details, but if you are interested, be aware that, in particular, these two Danish guys, Enevoldsen and Vistisen, describe these issues in articles, including that one from Anesthesiology published a couple of years ago. What does it mean? It means that in real life, actually, the predictive value is not that good. You see this paper, independent study done from the group of Marco Ranucci in Italy, reporting an area under the curve clearly better than what would give us a random guess, but it's more around 0.75 than above 0.9. And in practice, you know, for the HPI cutoff value of 85, the positive predictive value in this study was only 13%. This is a very recent paper published in Anesthesiology. Actually, it was published online last year, reporting a positive predictive value around 30%. So a positive predictive value of 30% means that 7 out of 10 alarms will be false alarms. And that's something we need to keep in mind because, you know, we are going to, if we start using these tools, if we start to use predictive analytics, we're going to move to clearly a reactive approach. I give vasopressors or I give fluid when the blood pressure drops, to a proactive approach, which is I give, I'm not sure what I should give, but I give something to prevent a hypothetical drop in blood pressure in 10 to 15 minutes. And if the predictive value is not that good, if I have 70% of false positive, that actually may be risky for my patients. I may give, for instance, vasopressors to normotensive patients who would never develop hypertension. Because, again, remember, when you predict hypertension, by definition, the blood pressure is still within the normal range. So the question is whether you should give or not fluid, vasopressor, or inotropes in this context. So it's basically raising more questions than providing answers, at least as of today. On the top of that, regarding HPI, we noticed that HPI is almost the perfect reflection of the mean arterial pressure. It's kind of obvious on these figure we published last year, and it comes from another publication. And you see at the top, that's the mean arterial pressure trends on the left, and then you have the HPI trends on the right. And you know, at first sight, it's not obvious that one is a reflection of the other because the scales are very different. But if you do what we have done, that you just adapt the scale to ensure you have the same scales for HPI and for the map, then you realize, particularly if I put it vertical, that one is the perfect reflection of the other. You can do that with many other papers published, and that's what I did for that slide. And then you realize there are actually multiple mirror effects published in HPI studies. So what does it mean? I mean, it's not only anecdotal. It means that HPI tells you that the blood pressure is close to 65, but has not yet reached 65, which is the cutoff value used to define hypertension in all these HPI studies. So you see in this example, as soon as the map is around 72, 70, I mean, this is a yellow zone on this figure, clearly the HPI variable is above 85, indicating that very likely the blood pressure will drop below 65. But you see, it's not always the case. In this example, actually never drop below 65. So what we know today is that this super sophisticated variable HPI we get from artificial intelligence is basically or gives us basically the same information as the mean arterial pressure. There are now studies, large studies published in good journals showing that as soon as the map is below 72, 71, HPI is above 85. So clearly, it raises the following question, can we predict hypertension with mean arterial pressure as well as we do with HPI? And we have today the answer because a few studies were published over the last 1 and 2 years. That's the first one coming from Korea, comparing the predictive value of the mean arterial pressure and of HPI in patients undergoing liver surgery. And you see that the predictive value, at least the area under the ROC curve, was exactly the same. And that's the most recent paper published in anesthesiology by a group from the Netherlands, and showing again that, yes, HPI is able to predict, has some predictive value, but the mean arterial pressure itself is actually as predictive as HPI. So, why using complex and expensive machine learning algorithm if we have the information already on the bedside monitor? By the way, in this study is pretty interesting because we could imagine the area under the ROC curve is the same for the map and for HPI, but one variable could be more specific than the other. But it's not even the case if you look at the curves for 10 minutes and 15 minutes, because it's more visible. In red, you have the ROC curve for the mean arterial pressure. In blue, you have the ROC curve for the HPI, and you see they are exactly the same. They are clearly superimposed, explaining that whatever the cutoff value you decide to use, you will get the same predictive value. So that's clearly disappointing. And one of the ways to explain that is that, machine learning algorithm may simply learn what clinicians know. I mean, that's happening actually more often than we think. They learn, but they learn what we know. And what we know is that when the map is low, let's say around 70, the probability it becomes very low. So below 65, because once again, this is a cutoff value which has been used to define hypertension in most of these studies. So the probability it becomes very low is higher than when the map is high. I mean, that's common sense. And this is also what machine learning systems are able to learn. A few words about cardiac output monitoring. I mean, many of you are probably using pulse control algorithm or pulse wave analysis techniques to compute stroke volume and cardiac output, calibrated or not calibrated. But even if you use a calibrated system, between two calibrations, I mean, you will rely on your pulse control algorithm to track changes in cardiac output. Obviously, if you have an abnormal blood pressure waveform, either underdamped or overdamped, you may have the best pulse control algorithm in your hemodynamic monitoring system. You will end up, or you may end up with wrong stroke volume and cardiac output values. And abnormal blood pressure waveforms are very common. There are studies showing it's about 1/3 of critically ill patients who have abnormal waveforms if you look at them carefully. So the good news is that there are algorithms, and in particular machine learning algorithms, which have been trained to detect abnormal waveforms. And here the example of a study we published last year was the team of Stefano Romagnoli from Italy, where we used an electronic filter able to automatically detect underdamped waveforms to correct abnormal waveforms. And we assessed the impact on cardiac output measurements. So for the study, we selected 70 ICU patients who had confirmed underdamped arterial pressure waveforms. And here you see an example of a typical underdamped waveform with a clear overshoot at the beginning and then multiple oscillation. It's not always that obvious, but we confirm that all waveforms were underdamped using the Gardner reference test. And then we use this electronic filter, which is able to normalize the blood pressure waveform. And we compare the cardiac output measurements before and after filtering and you can see the results. So on the left-hand side, you have the cardiac output measurements before filtering in these patients who all had underdamped waveforms. And then you have the values with the electronic filter. And also on the far right, you have values with a mechanical filter. We also use the mechanical filter in the study to get a reference for the publication. And you see a significant difference. And actually, we can claim from these findings, from these results, that underdamping, at least in this patient population, was responsible for 80 to 90% overestimation of cardiac output. So it's very important to filter blood pressure waveforms. And I think that's also something that we will have pretty soon at the bedside, thanks to sophisticated software and machine learning algorithm. Hemodynamic profiling. So you may have seen this paper. So they don't call them phenotypes or profiles. I mean, it's endotypes, but it's the exact same thing. The idea is to ask artificial intelligence to classify hemodynamic profiles, to identify, to discriminate between patients with hypovolemia, patients with cardiac dysfunction, and so on and so forth, using, of course, hemodynamic variables. That's something, many of us started to do many years ago. I remember when I was a resident, I had a textbook in my pocket with hemodynamic profiles described from the Swan-Ganz catheter measurements. You are all familiar, I'm sure, with these kind of tables. We can do the exact same thing with the variables we measure from pulse wave analysis techniques. And here you have the example of the different profiles we can describe in patients with systemic hypertension. So hypertension can be related to vasodilation, or it could be a decrease in cardiac output that could be related to bradycardia or to hypovolemia or to cardiac dysfunction. So in this study, once again, they asked machine learning algorithm to do the job. And indeed, the machine learning algorithm was able to do that automatically. Having said that, when you look a little bit more closely at the results in the bradycardia group, which was group number 2 in that study, you see that yes, the median heart rate was below 60, but obviously some patients had heart rate above 60, even above 70 in the bradycardia group. And that's not a mistake that any clinician would do. Same if you look at the vasodilation group, the group 4. I mean, if in some patients SVRI was low, obviously in some patients it was in the normal range, even above the normal range. And once again, I don't know any clinician who would claim that a patient has vasodilation and needs to receive vasopressors if SVRI is above 2000. So just to say that these machine learning algorithms make mistakes as well, and are not always as intelligent as we would like. We make mistakes as humans, of course, but not the same kind of mistakes. Usually we make mistakes when, we are multitasking, where we are super busy, when we forget something. Machine learning algorithms make different mistakes. They are not always able to differentiate or discriminate between 2 different patterns. And I like this example. I think a computer that would be trained to discriminate between a blueberry cake or a puppy would probably make some mistakes from time to time, but no human being. I think you could ask any kid to look carefully at the picture, and no one would say this is a cookie if actually this is a dog. On the top of that, I think today we are lucky enough. We have more and more hemodynamic monitors helping us to understand the determinants of blood pressure at the bedside. This is here just one example where you see the map that depends on cardiac output and SVR, cardiac output that depends on stroke volume and heart rate. And stroke volume, if stroke volume is low, you can see if the patient is fluid responder or not. And so if it makes sense to use fluid or to give inotropes to improve stroke volume. So we have these kind of smart visual decision support tools, meaning I'm not sure we need sophisticated machine learning algorithm to analyze, by the way, a small number of data. You know, machine learning algorithms are designed to analyze big data when it goes clearly far beyond the capacity of the human brain, but to integrate 4 to 5 hemodynamic variables, I really believe it's not necessary. Then I'm going to conclude with POCUS evaluation. So I know you had a lecture already on ultrasound, but I think it's a field where AI may be very interesting. You know, ultrasound technology dramatically improved over the last, I would say, 20 years from these very odd machines to very small devices. Now, many residents have a probe, a wireless probe in their pocket. They can connect to a smartphone. There are many different devices on the market. They all have advantages and limitations. I have no time to discuss it now. But clearly, AI, it's not only hardware improvement, it's also software improvement with AI invading ultrasound devices. So here is an example. The system will help clinicians to correctly position the probe, will grade the quality of the image, and will automatically label the heart structure. It's maybe not super useful, pending you have basic training in echo, but it's just to illustrate what could be done with AI. What's more interesting, in my opinion, it's when these devices, when these algorithms are able to do the measurements automatically for you. For example, if you want to quantify the subaortic VTI to estimate stroke volume quickly with echo Doppler, there are artificial intelligence software that are able to automatically detect the left ventricular outflow tract and to position the caliper, record automatically the velocity time integral, calculate the average value over a 4 seconds period, and give you a subaortic VTI in 15 seconds. This is a study I did with colleagues from Lisbon, Dr. Philippe Gonzalez and others, where we asked trainees and experts to use this kind of algorithm, and we compared the VTI measurements to manual measurements done by experts. And you can see the trainees actually were doing a pretty good job with a percentage error of 26%, which is actually what we expect from any system measuring or useful to measure or estimate cardiac output. That's another example. Here is automatic detection of border detection, continuous automatic border detection. Sorry for the noise. And you see that it's an automatic calculation of LVEF. Here you have a different patient with obviously a decrease in left ventricular ejection fraction, 26%. So it's done with AI again. And what's interesting as well is that this software are able to give you a feedback regarding the quality of your measurements. And you see here, typically on the far left, it's red, so it's not good quality. You cannot rely on the measurements. By the way, in that case, the machine will not even give you the values. In the middle, it's yellow. You will get a number, but be careful with the interpretation. On the right-hand side, you have good quality measurements. You can rely on LVEF measurements. That's also something we assessed with the same colleagues from Lisbon in this paper. Was published in Critical Care 2 years ago. And again, we asked experts and novices to measure LVEF with the AI system. And we compare to reference manual measurements done by the experts only. And you see that we got pretty interesting results. And what was actually pretty fun in this study, that the reproducibility of LVEF measurements was actually better for novices using the machine learning algorithm than when measurements were done manually by the experts. Okay, so that's interesting, I think, to realize. Having said that, all systems have not been created equal. We did another study with a different system. It's a very appealing system. Some of you probably know it's a crystal-free ultrasound transducer, so it's really affordable. You can connect to a smartphone, and there is an algorithm on board as well for the automatic measurement of LVEF. We did a comparison study again. You see a significant relationship, but weaker than with previous systems, and pretty wide limits of agreement, meaning I would not recommend it to assess automatically LVEF. By the way, on the top of that, fully automatic LVF measurements was possible only in less than half of the study population, meaning obviously that one is not yet ready for prime time. So AI is not always the ultimate solution for all problems in medicine and also for all problems in critical care, and particularly for ultrasound. Do not consider that all systems have been created equal. Just look at publications, test yourself if you have this opportunity, some of the systems coming to market, to make your own opinion before adopting them. So in conclusion, regarding AI and hemodynamic monitoring and management, regarding blood pressure monitoring, I told you, I think we'll use more and more in the near future pulse oximeters, not really to measure absolute values, but more to track changes in blood pressure between intermittent measurements done with brachial cuff. AI to predict hypertension, raising so far more questions than providing answers. You know, what is the real predictive value in real life conditions? Can we treat probabilities knowing that the probability is more around 60, 70% than 100%? If you are interested in the topic, I mean, this is part of the very last issue of anesthesiology. You have 2 articles and 1 editorial explaining that, unfortunately, HPI is not a better predictor of hypertension than the mean arterial pressure. Cardiac output monitoring, I told you, if you use pulse control algorithm, it's going to be very useful to use filters to ensure we analyze, or these algorithms analyze, a good quality blood pressure waveform. Otherwise, your cardiac output measurements may be wrong, and AI may help us to filter blood pressure waveforms. AI to identify hemodynamic profiles. Yes, it's doable, but it makes mistakes, and it's so easy to use. And it's so easy to do, to integrate 4 to 5 hemodynamic variables together. And on the top of that, some of you have smart hemodynamic monitors presenting the variables in a logical way that I don't think we can justify the additional cost of AI technologies just for this specific purpose. And finally, AI for POCUS evaluations. I mean, you understood that that might be useful, particularly for novices, for people who have not much experience. But once again, be careful, all systems have not been created equal. With that, I thank you very much for your invitation.